Okay, so what we're going to discuss here is the intermediate value theorem, which is really known as an existence theorem. Okay, and this is an extension of continuity, and this is known as an existence theorem because we're not asking you to specifically find a value. We're asking you to show that something exists, and that's it. But there are some steps that you have to use to prove that. So in the intermediate value theorem, or as it's known as the IVT, there are some conditions that must be met before you can even use it. So first of all, you need to state a hypothesis, and what you would state that is that your function f or g or k or whatever you name it is continuous on the closed interval from a to b, meaning two values on the x-axis, and if k, meaning a y value, so this is a y value, is some given number between f of a and f of b, meaning if I know what the function is and this is a given x value at the beginning of the interval, when I plug that a value into the function, I'm going to get the corresponding y value, meaning I have a point a comma f of a, and then when I do the same thing with b, I'll be getting the point b comma f of b. So they are points on the graph. Okay, so what we have here is this continuous function from a to b. So here's my continuous function. This is f of x. Okay, and this could keep going in either direction, but what they're saying is we're only looking at this portion of the function. And then you have the point a, f of a, and b, f of b. Then the conclusion is saying that there is some y value in between these two y values that because this function is continuous, this graph will cross at least one time. The intermediate, meaning going from A to B, I'm going to cross this value, this y value. So they're marking it with a horizontal line, knowing that you're going to cross it at least once, because you could cross it more than once, but we only care about it crossing one time. So the conclusion would be that there is at least one given value c, meaning we need something to plug into the function to get that y value, that falls between a and b, such that when I plug this c value into the function, I will get its corresponding y value. Okay, so I'm going to show you how to prove that. But first of all, when you're using the IVT, you must state the hypothesis and the conclusion. When you're using the IVT, you must state the hypothesis and conclusion in this fashion, meaning you would state hypothesis, f of x, or whatever the function is labeled, is continuous on the closed interval from a to b. These will be numbers. And you can state because, meaning it's a polynomial, but it's not necessary because sometimes in the problem it will state f of x is continuous. So you don't even need to state because the problem told me so. No, we don't care about that. You state the function is continuous on the closed interval from a to b. If you have a reason because it's a polynomial, whatever, that's fine, but this is optional. Since you have so much more to remember, I would forget about this. Just state that the function is continuous on the closed interval. And really what you're saying is this y value, f of a, will be less than k, meaning it will fall below this k value, and f of b would then be greater than k, meaning up here. Now, one thing you need to keep in mind is the inequalities could be reversed. Meaning this value could be above, meaning up here, and this value could be below, meaning the function is decreasing. Just as long as they flip over, and I'll show you what I'm talking about when I do a numerical example. So once you've made this statement that the function is continuous, you're going to do the proof with the math, okay, and then you can state the conclusion. By the IVT, there exists at least one value c on the open interval from a to b, such that when I plug in that c value, I will get the given k. All right, the question I always get is, why is this open? Because when you plug in these values, you know that they're not going to be this value. Okay, with a bunch of letters, it doesn't make sense. Let's see what happens when we actually do the math. So here is a very basic example. So it's saying if f of x is this polynomial, show that there is some given value c on this closed interval such that f of c is equal to 10, meaning this 10 represents this value here. So what we want to prove is that when I plug in 2 and I get some given y value, and I plug in 3 to this function and I get some given y value, when I plot the points from here to here, I will cross 10, meaning this value is going to be our 10. So how do I do that? Well, first of all, we know this function is continuous because it's a polynomial. There is no place where this function is undefined. So in my hypothesis, I will state f of x is continuous on the closed interval from 2 to 3. That's it, period. Now, I need to prove this portion right here. Okay, this is a bunch of letters. Now we're going to do it with numbers. So what you do is you evaluate f of 2 in here. So this is 2 cubed minus 2 squared plus 2, which is 8 minus 4 plus 2. 8 minus 4 is 4 plus 2 is equal to 6. What do I do with this 6? I want to compare the 6 to this k value over here, this 10 that we have in our problem. And what I'm looking for is 6 greater than or less than 10? In this case, 6 is less than 10. So now I need to use the other x value in my interval, f of 3. So I plug in here, 3 cubed minus 3 squared plus 3. 3 cubed is 27, minus 9 plus 3. 27 minus 9 is 18, plus 3 is 21. So this is equal to 21. Now I need to identify, is 21 greater than or less than 10? And what I'm looking for is for this inequality to be in the opposite direction, meaning this is actually greater than 10. So if you go back here, see how this and that they're flipped. That's exactly what you want, because what we're saying is one value is below and one value is above. So when I plot the point 2, 6 and then I plot the point 3, 21, I will cross 10 when I connect those dots, meaning here's your graph. This is the point 2, 6, we'll say. So this is 2, this is 6. I'm going to plot. Okay, then I have the point 3 and 21 is all the way up here. Okay, this is 3. So then there is that value between 6 and 21. This is a y value, this is a y value. So that means 10 would be about here. So in order to connect those two dots, whether I have multiple times where that graph crosses or just one, from here to here, I cross at least once. At least once. Okay, because this is a continuous function. Okay, so what I need to state in my conclusion by the IVT, there exists at least one value, and they use the variable c here, on the open interval from 2 to 3, okay, because we know that this can't be 2 and this can't be 3, because they already have their corresponding y values, okay, such that f of c is equal to, and in this case it's a specific value, 10. So in this case, right here, this number will be specific to your problem. Oops, specific to your problem. Okay? So it's not always going to be 10. It could be something else. So you need to read the problem carefully. So that is a basic example of the IVT.